Okay, so in this video, I'm going to be going over the basic process of how to make a glider for the Red Bull Flugtag competition. So the first step I'm going to do is I'm going to start creating airfoils in XFLR and then testing their viscous performance. So I'm going to use the 2412, which is a good aerodynamic standard. Then I'm going to also do the 4412 and 6412. I'm going to generate these because they'll be able to generate more lift at 0 degrees angle of attack, which is kind of what I want for a good flat flight path glider design. And then I'm going to do another one in the middle, but make it slightly thicker, so 44, 30, 20. Yes, and then I'm going to go to the direct analysis. So, before I proceed, I'm going to need to estimate a Reynolds number. So the easiest way I think to do this is just to go to the wing and plane design in XFLR, create a new plane, turning off elevators and fins, and defining a main wing. So the chord doesn't really matter, so I'm going to just set it to 2 meters. So I'm going to estimate the width, or the chord, of the glider I'm going to make is going to be about 16 inches. That's just an approximation to start off with. So I'm going to set both those to 0.4 and select whichever airfoil, save it, and then run an analysis. Actually, I'm going to turn off the offset just in case. And so, looking here, the average human running speed for a male is 8 miles per hour, and in meters per second, that's 3.576. So if you can jump off at a sprint and you assume that I'm going ever so slightly faster, I'm going to go with 4.5 meters per second. And make sure viscous is unchecked. So save that. And so if I run that analysis, and I go to the span-wise analysis points, you can see there's a Reynolds number of 120,000. So I go to the direct analysis, and I'm going to run each of these at an analysis value. Type 1 for ease, 120,000. And in Mach, that would be equal to just the the meters per second, which was 4.5 divided by 343, which is a Mach of 0.013. And I'm just going to keep these constant. And just going to repeat that for all of my 4 airfoils that I want to test. And I'm going to run this at a sequence of -1 to 1 degrees. With a change of 0.2. So again, I'm going to be flying it mostly flat, and I just want to see how it performs in those ranges and get some detailed responses, which is why my increment is so low. So I'm not too much worried about the coefficient of moment. I can fix that by balancing out masses. So I'm going to set this to coefficient of lift divided by coefficient of drag. And here we can see that the 6412 is performing much better in these lift over drag estimates here. And while worse at drag characteristics, I'm convinced that the sparing of lift will still make it more worth it. Because here you can see it's about 25 for lift over drag here. So yeah, we get a far greater advantage in lift than cost we do in drag if you compare the ratios for both these powers. I haven't run a MATLAB analysis yet on optimizing it. That will be shown later. This is more a basic approach. So going off that, I like the 6412 for my analysis. So I'm going to go to the wing and plane design and create a new plane. So for now, I'm going to turn off the elevators and fins still and use the 6412. And setting the chord to 0.4 meters. That's 0. And going to add a inertia value roughly equivalent to my mass. So I'm going to estimate that at 63.5 kilograms. And just to increase its ability to be apparent, I'm going to set these at -1 degree and 1 degree, and this at 0.5. And so going here, we can see that only just about 4 newtons of lift are being generated at 0 degrees. That's a bit lower than I would expect, so instead I'm going to go with an estimate of 15 miles per hour as like the sprinting speed, basically. And so I got to redo that process. So editing the analysis to have a meters per second value of 7 meters per second. Yes, and so we can see the new Reynolds number is 187,000 approximately. So I'm going to delete all my old analyses and rerun them each. Changing the Mach value to 0.02 and the Reynolds number to 187. And so here we can still see the better performance of the 6412 at low angles. So going to increase the Y span to 3, keep the chord the same, 6412. And I'm going to add a tilt angle of -1 degrees, or sorry, 1 degree, in order to slightly increase the lift coefficient. And going to recreate the analysis at 7 meters per second. And so here we can see we're generating approximately 46 newtons of lift. So we still need more lift force. So if we look at the direct analysis, we're going to calculate a more theoretical value for this. So the coefficient of lift we're getting at, we'll go with 1 degree, is 0.78. So if we multiply that by 1/2, and then times 7 meters squared, and then times the area of our wing, which is equal to 3 meters times 2 times 0.4. And then multiply that by the density of air, we get 57 newtons approximately, which still isn't enough to even really come close. Perhaps we should look into flap designs then instead. So I'm going to just create flaps for the 2412 and 6412. So from past experiences, I know typically to stick to 30% of the chord for the flap and 30 degrees. And so here we can see we get a much higher coefficient of lift, around 1.53 for the 6412 flap design. So we're going to run that in our wing and plane design editor. And we're also this time just going to increase the chord. This is going to differ slightly from our predicted Reynolds number, but it's still within a similar range of magnitude, so it should be accurate enough. And so here we are now generating around 240 newtons of lift, which is pretty close to what we're looking for. So, given my approximate weight, we would need 580 newtons in order to not fall at all. And so obviously we're not going to be able to fully achieve that, but we are still nevertheless looking for a bigger return. So we're going to go back to our X-foil direct analysis and look at how the characteristics of the flap design change with certain angles. So we're going to go to the 6412 flap and add some data points to get it from 2 to 6 degrees. And so here we can see it's really peaking even here at 4 degrees. And if we zoom out to the coefficient of lift, we're starting to basically see no greater returns after that. So if we go to our wing and plane design, plane edit, and set a 4-degree tilt angle, then we can see it's going to generate 270 newtons of lift. We're going to look at stream values, and we are seeing some pretty big curves here. So this is suggesting that we may be losing a lot to induced drag, and wingtips might be an important addition in order to maintain our lift. So we're going to check out what our induced drag induced angle looks like to see how much we're losing in lift. Keep it just at 0 degrees. Yeah, so we're losing a lot of angle here. So I think wingtips are definitely a good addition. But I am starting to like this design anyway, so I am going to keep it for now and test it in ANSYS to see what values it can return. Okay, so in order to create that in SolidWorks, we are going to go to the direct foil design. Just going to make all these invisible to make it clear. And we're going to export this as a DAT file. So now we have the DAT file here. We're going to copy it just so we don't accidentally corrupt it, and then force it to be saved as a TXT file, change it, and then open it. And here we can see all the various values that will help us design the airfoil. So we're also going to create an Excel document and call it 6412 Excel. And we're going to copy all these numbers here and go here. Paste the numbers in, go to Data, Text to Columns, Next, Space, Next, and Finish. And so then we're going to adjust the numbers and then add a bunch of zeros into this third column. And just going to copy and paste a bunch until we fill out all the rows. And once we have that done, we're going to highlight all of this all the way to this top part here. And we're going to copy this just into a another text document called 6412 finish. And you can just go in directly, paste. And with only a slight bit of editing, you can now see that they're all lined up and in place. You have to make sure that all these zeros are lined up correctly in order for this to work. Now you can export that to your drive or the cloud and somehow bring this on a computer that has ANSYS. Yes, so now I'm in SolidWorks, and I'm going to create the flapped 6412 design in SolidWorks, but I'm also going to add wingtips in order to prevent induced angle. So I'm going to go to curves, curve through XYZ points. May not have fully downloaded. Okay. Okay, and now we're going to create a sketch on the same plane as it, which is the front plane. And we go to convert entities, select that, and then click yes. And since it's already so detailed, we're just going to create one straight line between these two dots and exit the sketch for now. Now, we wanted a chord value of 0.6 meters, so first we got to evaluate the measure of our current design. And so here we can see it's about 0.94 inches. We're going to change that to meters, or millimeters. Yes, so we want 600 millimeters, but we currently have 23.82. So that means we're going to want a scale factor of about 25. So we're going to go to Tools, Sketch Tools. Sorry, I need to be in Editing Sketch. Scaling about the origin, and the scale factor set to 25. And OK, and then exit the sketch. So we're going to then extrude this sketch 3 meters to both sides. And now we're going to create a sketch on here. Like this. And then we're going to smooth it out using an arc shape. going to extrude that just a few inches, just 1.5 inches. It can still be very thin. We just want a solid wall covering the, separating them and make that visible. And then we're going to do a mirror pattern, and we're going to mirror this feature over this plane, and now we have it on both sides. So we're going to save this as, in our documents, as test Flugtag design 1. And now we're going to load up ANSYS multiphysics and then go down to the workbench. Currently, we're just working on the aerodynamics aspect. Later, I will get into the structural element. So we're going to do a fluid flow CFX and open up geometry file. Yes, so now we're going to go to File, Import External Geometry File. Oh, right. Forgot one step. We need to save this as a step file. So we're then going to generate that. Okay, that did not work. I'm going to inspect to see if there's anything wrong with the geometry itself on our SolidWorks file. No, it still looks fine to me. We're going to try importing it again. Or actually, we're going to attach it to a CAD file. Oh, there's the source. I was looking for that, that's why I ran it knowing it was not fully developed. So we're going to attach to that one and then generate. Okay, there's no compatible file. Interpreter. Going to try importing again. Okay, so we're going to try and save this as an IGES. And then import that. That works. Cool, so we now want to select as many faces of our design as we can. We want to see as much turn green as possible, then we're going to rotate it and select some of the faces on the back. Yep, so that should be enough of our main ones. So we're going to right click, go to name selection, apply the geometry, and we're going to name that surface glider and generate the geometry of that. And now we're going to go to tools, enclosure, and we're going to generate that. And I'm going to zoom out of it and evaluate how much space we need on each side. And so I think we have some extra space in both x directions, so I'm going to lower that. Primarily in the negative x direction, and regenerate. Yep, and so I think that's a good enclosure space. And we're going to go create a Boolean, make a subtract, target the enclosure, and use our design as a tool, generate one part, one body, save. Yes. Okay, that's good. So we're going to refresh the mesh. Great, and now we can double click and start editing the mesh. So we're going to try generating the mesh with the default settings. so I think the length of this mesh is having me a bit concerned that I made the enclosure too big. And also I want to re-edit the geometry because I didn't initially have it tilted by those 4 degrees. So I fixed all that, and I'm gonna redo those steps. Okay, so now we have successfully generated our mesh by changing around a few of our meshing details. Okay, and we want to double check that that's saved because this takes so long to run. I'm going to exit out of it and also close my geometry file and update the mesh. Great, and now we can work on the setup. And so remember, we were going with a velocity approximation of 7 meters per second. So we're going to insert a boundary, aim at inlets, and we're going to select this space for our inlet, apply, need to set the normal speed to 7 meters per second, insert boundary, aiming at outlet, select location box, select the back, boundary details, relative pressure of 0, apply, and OK. Now we're going to insert boundary, we'll include walls, wall, location here, 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 and here. It will be a free slip wall, and that's it. And finally, we'll insert a boundary called glider wall, wall type, setting it to the faces of our glider. Boundary details will be a no slip wall due to the no slip condition, and it will be a rough wall with a standing ring roughness of 0.007, which is still low, but we want to keep that to account for friction. So we're going to save that. Then we can exit out and then run our solution. This solution step is going to take several minutes. Yes, and now we've successfully run it. So, going to go load up our results. And here we can see the lift direction is going to be in positive Z, which may be different from some of my past ANSYS builds. So just so we can see what we're looking at, I'm going to generate a contour of pressure with 100 contours. Yes, and here we can see we are successfully generating high pressure and low pressure. So we're going to save that. And another thing we were really concerned about was if there was going to be curling over. Yes, here we can see. I'm going to reduce this factor here. Sorry, increase it. I'm going to go with 4. Here we can see that there is still some flow over, but it is very light. So we're going to treat these wingtip designs as successful. Good, good. And now we're going to check the solution reports and go over to our report viewer. Remember the lifts in positive Z. Yes, and so the total force here we can see is approximately 367 newtons. That's going to be our unit. You can see meters per second. So that is a very satisfying result for now. So I'm going to save that project. And we're going to close these. And so I guess now I will go over the process I'm planning for on a structural analysis of this design. I'm going to ignore the wingtips for now. So I'm going to create a new part. Actually, I'm going to start off from this design, just since it's easier. Structural 6412 design. Yes, so it saves the previous one as was before, and I'm going to delete these 3 elements. So I can start over from my sketch. And I'm going to add some things to it. I'm going to create 2 1-inch you got to make sure the size is fixed in place for the overall width of this. And then I'm going to set this to 1 inch in diameter. And create a second one of those. And put them 1 inch apart from each other. There, make them horizontal with each other. Actually, with that, 3 inches. And then put the front one back from the tip, 4 inches. 5. Yes, and so now I'm going to extrude this by 1/4 of an inch and create a linear pattern. So our previous design was 6 meters in total. Which is going to be approximately 236 inches, or about 20 feet. So if we space each one out by 6 inches, Stretching direction 1 is this. We make there be 40 of them. Sorry. Not use a linear pattern, we should instead use so bodies instead, selecting that. Direction 1 is that one. And now we successfully made it. And so now we're also going to create a carbon fiber rod substitute. So sketching out the front plane. Gonna make it 1 inch in diameter. So on the outside and on the inside. I'll go with 0.7 for thickness. And then extrude that a total of 20 feet. And then set the material to the first carbon fiber and save that. And for our material on this, we will go with a wood. I'm thinking pine. And so save that. So that's saved as structural 6412 design, and now I'm going to create a part called plastic cover. And once again, I'm going to delete these parts. And I'm going to edit the sketch. Going to remove those. Create a point near the center. Edit the sketch. And create a copy of that sketch. Edit the copy. And I'm going to scale it about the center by 1.02. So it's going to be slightly thicker, slightly bigger, but not that much. However, this is slightly concerning, the way it does not quite overlap properly with this line here. So we're going to create a point here. And so we're going to trim it closest on, nope. And so we're just going to follow the path similarly, but always making sure to be outside of the bounds that we created for the original line. So it should be bigger than the original sketch everywhere. And so now we're going to create an extrusion using this outer one and create an extruded cut using the inner one, which was unedited. And so we have a very thin sheet here, but we also want to edit this material to a plastic. ABS, applying that, save, and we're going to create a new assembly. Okay, now we're going to insert the carbon fiber rod, and we're going to make this here. Okay, and we're going to insert another carbon fiber rod. So we lock that in place. And now we're going to insert the plastic cover. And now we're going to lock these two relative to each other. And then we're going to save as a symbol Flugtag 1. And we're going to save this as a step and an IGS file, both of them. So we're going to edit the geometry. So we're going to import an external geometry file, going with the symbol Flugtag IGS, and generate that. Okay, so we're going to save that. Exit. We're going to refresh the mesh step, or model in this case. And now we're going to edit the model. So we're going to solve for the mesh. You can see the different colored ribs of the design. Almost done. Oh, no. Yes, we got the physics. So we're going to try that again with the new settings. Yes, I think you can see here it's mainly on the outer part, the sort of very thin wireframe that's not working. We'll try a linear order. Yes, so now we have successfully generated our mesh, and we can move on to adding forces. And I'm going to change the display back to the shaded edge. So on the environment, we're going to add a pressure. Okay, so I'm going to display a shade exterior. And we're going to hide this body so it doesn't appear. Now we're going to apply a line pressure. We're going to save that. And so we're going to go back to our model. Okay, I'm gonna come back to this project later in another video. That's all I have for today.